All right, on to the modern approaches. I like this part. I do want to give a shout out to Craig Enders at UCLA. Um, Craig wrote a fantastic book on missing data. It is really, the definitive piece, and a lot of the material I'll present comes from lectures that Craig himself has given. I happened to be giving a workshop at Portland State, and Craig had been giving a workshop the 2 days before. He left all his files on the computer. So I took them, and when I saw him the next time, I had a laugh with him about it. So it's but that's where a lot of this stuff comes from, and that stuff has been fantastic learning material for me. All right, first approach, I call this the gateway approach, stochastic regression. It's the same as regression imputation, but what it does is it adds a random error to each of the estimates. So you're not sitting right on the mean of that group. You're somewhere, somewhere off from it. That addition of random error really, really, really helps to address some issues, but not all of them. I call this the gateway approach because it's a piece of something bigger that we'll see, but it starts to give us a strategy. If you see the imputation results, you can see stochastic actually does pretty good in this example. However, I would caution I would use this example with caution. With stochastic, because it's a single estimate with that random error, you can get really weird ones. I've seen ones that are pretty far off from what they should be. So maybe 1 out of every 15 or 20 is going to be problematic. So that's the biggest issue with stochastic, is that it's just a single point, and if you get some weird combination of random error, then it's going to be pretty off. All right, multiple imputation. This is one of the two biggies. If one estimate's good, then multiple estimators are better. If we have 20 estimates, if one's weird, it washes out, right? We begin with stochastic regression. This is what's generally called the I step. Then we fill in those predictions, add the random errors. And then we have the posterior step, which is where we generate new estimates of the mean and covariances, and then go back to the first step. This is basically some Bayesian stuff with Markov chain things going on. We don't really need to understand what's under the hood here. It's pretty complicated. But you basically end up with a different mean and correlation or covariance structure. Then you go back and estimate again. You do this over and over until you hit the desired number of new data sets, and that's usually 20. We run our analysis on each of the data sets, and we pool the results. This is computationally intense, but what used to take several hours might just take a minute or two, depending on software and, of course, how large your data set is. I've done some back in the day that took maybe half a day. But you're not going to run into those sorts of pieces anymore. So multiple imputation has been made very well. As you'll see, it's been made pretty simple by our software. So here's just an example of the sort of thing that you would get. And again, I said generally we would have 20 estimates, which is kind of the standard. I just show 5 here, just so you can see you're getting a different estimate each time. And then we are just going to average those basically and do an analysis. Simulation studies that have been literally out for good 30 years or so show that multiple imputation outperforms every single imputation approach that we've looked at so far. Yeah, and when I say modern techniques, I will add that some of these techniques are over 50 years old. So you can see multiple imputation does a really good job of matching the actual distribution. We're pretty darn close there on all of those. One thing I like about multiple imputation is it tends to, in my experience, slightly underestimate the effect size, which makes it a more conservative technique. And in this context, I always prefer conservative over liberal, not in other contexts, but in this context, certainly. All right, maximum likelihood. Maximum likelihood actually doesn't involve imputation. It involves modifications to the full data formula. And what this means is that full data isn't required for estimates of parameters. And I believe it was Fisher who first introduced this maximum likelihood approach that has a tremendous number of applications. Uh, it repeatedly auditions population values until it finds ones that best fit the data that we observe. It's similar to multiple imputation in that it involves a two-step process. The E step builds regression equations, and then the M step applies calculations to the filled-in data, estimating the means and the covariances. And then those means and covariances go forward and are used for our final estimate. This continues until estimation has stabilized. So this can spin for a little while. Again, it's been available for well over 50 years. In psychology, it's generally been associated with latent variable analyses and is really only implemented in those protocols. I don't know why that is. It just happens to be how it is. And you can see the ML results do a really good job at estimating the effect size, the actual effect size, mean and standard deviation. Maximum likelihood performs about as well as multiple imputation. There's small differences. However, it's often recommended as the top choice because it requires fewer assumptions. We'll see that we don't need to do any diagnostic checks here. And it's also available for situations where we can't assume multivariate normality. We combine maximum likelihood with all kinds of other robust forms of estimation. So when we can't meet our assumptions, we can use maximum likelihood with some other stuff that's also generally available in structural equation modeling software. All right, to summarize, maximum likelihood and multiple imputation are the best. Both work well for MCAR and MAR. Other approaches only work under MCAR, which is practically never. None of these are ideal for missing not at random, but imputation and likelihood would be the better ones. Again, we don't know if we've got MCAR, MAR, or MNAR, but if we use maximum likelihood or multiple imputation, we're always going to have the best approach. Oh, and one thing I want to mention that I may have skipped over, and there's a good blog post on this by Paul Allison, who's one of the giants in the field of missing data as well. Paul recommends that we always use maximum likelihood rather than multiple imputation. The reason why he suggests that is because maximum likelihood can be used correctly by even novice users. Whereas multiple imputation, you can use it, but you have to know a little bit about diagnostics. Now, that said, there are situations where you can't use maximum likelihood. So we really need both of these in our toolkit.